Hello 108 students, Mr. McHugh here with you. Going to go ahead and do 4.3, wrap it up on page 2. We've got 2 more application problems to work with. First one's going to be a mixture problem, and it's going to follow the exact same one that's on page 236 out of the textbook, so you can read along there. And let me read the problem to you here. It says, how many ounces each of a 5% hydrochloric acid and a 20% hydrochloric acid must be combined to get a 10-ounce solution that is 12.5% hydrochloric acid. Now in my class I always tease about this cartoon character called Dexter in his laboratory. He's got a sister named Dee Dee. If you've ever seen the cartoon, it's hilarious. He's a little short guy, she's a tall, older, annoying sister that drives him crazy, and we try to have a good time with it. So imagine you are Dexter down in your laboratory, and you need to take, you've got a 5% solution of acid and you've got a 20% solution of it, and you need to mix them up with the right amount of ounces between the two of them to get a 12.5% for your chemistry lab experiment that you're working on. Okay, now these problems, they take a little bit of work, they take a little bit of MSI detective skills here. Make sure you label your variables, define these. I see many students, they don't write what X is, what Y is. When you do that, your brain gets organized, you maintain order. X for me is going to represent the number of ounces of 5% solution, the amount. Y is going to be the amount of the 20% solution. Okay, now I like drawing the beakers. I'm a visual person, so here's a 5% solution beaker, here's the 20% solution. It's a higher concentration. Notice my mixture beaker is bigger. Okay, I'm trying to get the visual here. Usually in class I kind of go like that to represent 5%, 20% would be a little higher. But this is the acid concentration. How strong is the acid in here? It's a 5% mixture, 20%, this is much stronger. You know you don't want to mess with acid, so you got to be careful with it. Okay, so I look at this, and the amount would be X ounces of the 5% plus Y ounces of the 20 equals 10 ounces. That's a 12.5% solution. Okay, now that's my equation A that I've written right here. Equation B is, what is the acid concentration? Now think of this for a second. If I had 10 ounces of a beaker and I told you it was a 70% solution, 70.7 times 10 would be 7 ounces out of that beaker. Here at the top is 10 ounces, if you can mark it. Here's halfway at 5, here's 7. From here on down, this is nothing but pure acid in here, and this is H2O. Don't forget that when they say concentration, the other component element is water. Sorry if you're a chemistry major here, I'm probably not using the right terms, but you get the idea. Okay, now, what you got here is, what's the concentration? Percentage gets turned into decimal, so you move it 2 places to the left, it's 0.05. X, you're going to multiply it to get the concentration. 20% is 0.2 times the amount of that beaker, and now you need to get 12.5, which is move it 2 places back to the left, 0.125 times how many ounces? 10. Now when you multiply that out, that's actually going to be 12.5. okay, just keep that in mind. Okay, now I'm writing my second equation B. I wrote that out down here. Notice I'm being neat and organized. Now my goal here was, the way I wrote it here, I asked myself, what do I got to multiply equation B? You really would like to work with whole numbers, and if I would move that decimal, I'd have to go 2 places there. This would only be 1 and this would be 3, thus I multiplied it by 100. But in effect, you could multiply everything by 2 places 100, and that would take care of it. Okay, so what I did was I multiplied by 100. I moved the decimal 2 places, so here's my 5x. Move it 2 places is 20y. Move this 2 places because it was already 12.5. Don't forget that. That's kind of important. 12.5, 2 places makes it 125. Okay, watch your counting there when you're doing that. Okay, here's your equation A. Here's your equation B. Now what I did was I looked at this and I see X and I see 5X, and I just decided to eliminate the X variable, only because the coefficients are smaller. You could do the Y if you wanted to. So in that being my strategy, what do I need to multiply equation A to get the opposite of 5X? To get a minus 5X, and I multiplied it by that negative 5. So I multiply by -5 across the board of equation A, and here's the results. Okay, once you've done that, you're ready to eliminate equation A. You're going to add the two equations, add the columns. There's the 0. -5 plus 20 is 15y. -15 plus 125 gives you 75. Divide by 15 on both sides. Lo and behold, you find out y equals 5 ounces. Okay, that's the hard part of the problem. You're doing pretty good now. Now that you know it's 5 ounces, it seems almost kind of silly here, but equation A tells you to take x ounces plus y ounces equals 10. So if the 20% solution is 5 ounces, that's what you found. 20% was 5 ounces. X has to be 5. 5 plus 5 is 5. Now you could do the algebra, but you can do that in your head. But that's how you do it. You substitute in, solve for the other variable x, and you find out that you need 5 ounces of the you need 5 ounces of the 5% solution and 5 ounces of the 20% solution. Okay, so that's how you do those problems. Make sure you answer them in My Math Lab in the right order. Now I know in this case it didn't matter, but make sure you answer them the way they want them. Don't mix up your variables. Okay, one more problem here. Objective 4, we're going to tackle a motion problem. Okay, and motion problem, I want you to get into your car. I have a little smart car. Usually I tease everybody about me getting on Interstate 84. And if I'm cruising and I tell you I'm going to go visit Salt Lake City, it's 300 miles away, and the distance is 300, and if I'm going 75 miles per hour, how long will it take me to get there? Everybody in Idaho is great at figuring this out. Why is that? Because you are good at isolating your variables. The time that it takes is what? 4 hours. What did I do? Time can be represented by distance divided by rate. Think of it as an expression. Now that's a ratio. You take any distance, divide by the rate, you'll tell somebody the time. I ask people, how long does it take to get to Seattle? I hear 10 hours. People are doing this in their head intuitively. Okay, so let's go to the problem here. This is example 4. It's right out of the book here. It's on page 237. Okay, so they tell you there's a car and a truck. I let C represent the car speed, T represents the truck speed. Now look how I'm trying to get organized here. Now you read this problem. Let me read it to you real quick. A car travels 250 kilometers in the same amount of time. That is crucial to this problem, as a truck travels 225. The time is the same. Highlight that. That's a clue. If the rates of the car is 8 kilometers per hour faster than the rate of the truck, find both rates. Okay, so you read that, you got to get organized. And I like to use, distance, by the way, equals rate times time. How far do you travel? Based on how fast you're going by how long you drive. So if I'm going 75 miles an hour and I go for 2 hours in my little smart car, I'm going to travel a big whopping 150 miles. I got cruise control, so I feel pretty good I could do that. Okay, so let's go back to the problem here. Distance 250, truck 225. Get organized. Rate C and T. Time. How can you represent time? Distance divided by rate from down here. So 250 kilometers divided by C for the car, which is the speed of it. 225 is the distance of the truck divided by its speed or rate, which is T for truck. Okay, notice the symbology means that they are equal. That was from the problem. That's a key component. Okay, we're told the car is 8 kilometers faster than the truck. So let's write that as equation A. Speed of the car is 8 more than the truck. So therefore you put the plus sign in there. Equation B, I'm looking at it and I'm remembering this, that the time is the same. So I take 250C, which is the time of the car, is equal to the time of the truck. 225 kilometers divided by T. Remember, T is the speed of the truck. Say it over and over again, not time, speed of the truck. You could use X and Y for these problems too if you want. Now what I did now here is I got a proportion. When two ratios are set equal to each other, you have a proportion. You are allowed to cross multiply. 250 times T equals C times 225. I wrote it. You can reverse the order with multiplication, commutative property. Okay, now you've got equation A, equation B. I turn around here and I look at this equation B. I write it down, 250T equals 225. Instead of putting C for the speed of the car, guess what you represent it with? The relationship 8 more than a truck. You stick it in there and now you're on your way. You reach that point now where you've got this problem licked and that you now know you can isolate and find the speed of the truck. Okay, you've got some distributive work to do here. You can follow along there, 225T plus 1800. I minused 225 on both sides of T. I end up with 225, oh my word, excuse me, 25T equals 1800. Divide by 25 on both sides. Lo and behold, the speed of the truck is 72 kilometers per hour. What's the speed of the car? Add 8 to it because that's the relationship, 8 plus T, and you've got 80 miles per hour. Okay, there'll be a problem like that and a problem like the mixture problem and a couple of easy ones in there with distance to help you out. Okay, class, I have wrapped up page 2 of section 4.3 with you. I know you got a fair amount of work here in this section, but you'll do fine. Remember, put your MSI hats on. Be positive. I know you can do this. Okay, I will see you to start off chapter 5. Okay, take care. Bye.